Thank you. Thank you for the introduction. 저는 Yoichi Enatsu입니다. Today my title is as follows. I am from Tokyo University from Japan. And okay. 감사합니다. So first of all, I would like to thank the organizers and my collaborator as composed of 5 authors. So now my topic is divided into 3 parts, and we introduce 3 results. The first, we consider the global dynamics of the epidemic model with delays. So now the method to obtain such result is the construction of a Lyapunov functional. And in the final part, last part, if time permitting, we consider the dynamics of the free boundary problem for epidemic models. This is the agenda of this talk. In the next view slide, we consider the basic epidemic model, which is called SIR model. So now, the next slide, this is a very basic model which was proposed by Hescott in 1974. Here, as you may know, modeling of epidemiological phenomena model for has a very long history in the especially the first model for smallpox proposed by Daniel Bernoulli in 1760. So now this model has properties that the susceptible individuals here becomes infected, and the infected individuals become recovered. We sometimes call the variable R recovered or removed, but here we assume it is recovered individual. And this model is governed by linear incidence rate, which is characterized by the term beta st times I of t. So now, for this model, the global dynamics is completely determined by a threshold, which is called a basic reproduction number. Here we call the threshold R0 or R0. So the next view slide, we show the non-stability result of this model. This model has at most 2 equilibria, which is called disease-free equilibrium and endemic equilibrium. Here, the model has one threshold, as we mentioned, R0. So we have 2 important points. One point is that we have a basic reproduction number as follows. B beta over mu times mu plus gamma. And here, by applying this threshold, we obtain that the endemic equilibrium is globally asymptotically stable whenever it exists. So here, this is a non-stability result for ODEs. So today my topic is here, the stability of the endemic equilibrium when R0 is greater than 1. This is sometimes become very difficult question when considering delay differential equations. So now, after we have some 3 view slides to extend the model into the delayed model. The first extension is to incorporate the effect of a time delay. The model is as follows. Simply, the difference of the model is that IT is replaced by the term IT minus tau. On the other hand, this model is derived by an original system, which is composed of 5 variables, precisely S and I and R and susceptible vector and infected vectors. So now, for the details, we will explain later. So now, let's see the second extension of this model. The next extension is to incorporate the immunity loss of the recovered individuals. Here, the difference of the two models is that delta RT is you can find in the first and the third equation of this system. Here, delta denotes the rate of immunity loss for recovered individuals. And now, the third is that now we consider that the infection process is written by linear function. So now, motivated by the fact that the actual incidence rate cannot be concretely determined in the real world. So we consider that incidence rate by a nonlinear function as follows here. The difference of the two models is as follows. So now, in the next view slide, we show that the original model of this model. In fact, here, the time delay is incorporated only in this term. So now let's explain briefly by giving an original model here. So now, this is the original model, which is composed by 5 variables. S in addition to the variable SIR. There are 2 models, which denotes VS is a susceptible vector population, and VI is infected vector population. And we apply the approximation technique proposed by Professor Takeuchi, indicating that VIT is approximated by a constant number times I of t minus tau. So let's see the briefly show this is a paper. So like, excuse me, can you see this? This one. Okay. So now, by applying their technique, we can consider the dynamics of the SIRS model. In the first part, we introduced SIR model. So here is SIRS model. The difference is that the recovered individuals returns susceptible individuals again. So that's why we call this model SIRS model. Now we consider this is our main model. For the nonlinear incidence rate, we assume the following 2 hypotheses. Especially the second hypothesis is sometimes used from a biological point of view. In particular, these 2 functions satisfy these 2 hypotheses. In fact, GI is, for the case, GI is I over 1 plus alpha I. This incidence rate denotes that the infection force does not exceed to a constant number. In fact, here, 1 over alpha. So this is called a saturated incidence rate. And we note that these 2 incidence rate satisfies 2 assumptions. So now, the basic result is as follows. So now, as I mentioned in the for the ODE, now we consider that the endemic equilibrium exists uniquely when R0 is greater than 1. Now let us give a short proof. So this is just equation. So let's consider the graphical image. Here, we consider that the function h of I. Here, there are 3 points. The first is that h limit hi when I approaches 0. Then the value becomes positive. And the second is that h is strictly monotone decreasing. And third is that the limit of h when I approaches plus infinity, then it diverges to the negative directions. So we obtain the unique existence of the second element of the endemic equilibrium, I star. So now in the next view slide, now let's reintroduce our main result here. This is our main result. In fact, when delta equals to 0, that is for the SIR model, we obtain the complete stability result as similar as ODEs. That endemic equilibrium is globally asymptotically stable whenever it exists. And here is also new result. However, we established partial answer. R0 is greater than 1, and the partial additional conditions here. The proof is based on the construction of a Lyapunov function. So now let's see why such condition is needed. In order to prove that, we divide proof into mainly 2 parts. Here, the first, when gi is a linear function and delta equals to 0, McCluskey obtained a complete stability. So now let's consider the case delta equals to 0 and later delta is greater than or equals to 0. So now in the next view slide, we show the proof for the case delta equals to 0. So this is, now we show the U0 E star of t is a Lyapunov function. Here we need Russell invariance principle. However, the essence is to show that here the time derivative of this functional is non-positive. Here, now let's see that this third term plays a very important role to cancel the delay term. Here. Now, in the next slide, we consider the time derivative of the functional dividing by 3 parts. The first is here, the second here, and third here. So, as you may know, this term minus mu s times here becomes non-positive, as you may know. But the red colored part, it does not seem easy to determine the sign. However, the result, consequently, it becomes the summation of these 3 equations is non-positive. So now let's see the proof here. So this is an interesting point of the McCluskey's idea that the delay term can be cancelled effectively and the summation can be written only by the function g. So here, g is x minus 1 minus logarithmic function of x, which is non-negative. So now here, by lemma 3.1, we obtain this result. So now let's give a quick summary. When we consider the case delta is 0, and the result is here. So the next, we prove that this gy tilde minus gy tilde t is non-negative. In the first part, we assumed the two hypotheses for the nonlinear incidence function, g. So in the next view slide, we show the inequality by applying two hypotheses. This is also the key lemma for the case delta is 0. Here, by using the assumptions h1 and h2, we can obtain such inequality. This is an abstract of the proof for the case delta is 0. So this is a proof for the SIR model with delays. So now we show the Lyapunov functional for the case delta is positive. Here. So this is a proof of our main result. When delta equals to 0, this red term vanishes. Similar to the previous discussion, we show that the time derivative of this functional is non-positive. The calculation may need a long time, so let's sum up. Here. So this is also the idea. So by using the relation, we obtain such inequality. And here, let's recall that this was the additional conditions. So when mu s star minus delta r star is greater than or equals to 0, then we can show that this u delta e star of t is Lyapunov functional. So, and by applying Lassalle invariance principle, we can prove that the largest invariant set, which the time derivative is 0, consists only of the endemic equilibrium. So here, this was the main theorem. In fact, the difference of SIR and SIRS is that delta is 0 or delta is positive. This is the difference. SIR, SIR model is delta equals to 0. SIRS is delta is positive. So now, this lemma indicates that for small delta, we can prove that the endemic equilibrium is globally asymptotically stable. However, there is still an open problem that when R0 and delta is larger, then endemic equilibrium is globally asymptotically stable. We still do not know the answer, but we know that this E star is locally stable, locally asymptotically stable. So this is the first part of the talk. And now let's consider that the case Gi is non-monotone. For the first part, we applied functional technique under the assumption that G is monotone increasing. On the other hand, when G is non-monotone type, we could obtain another bifurcation result. In fact, consider the incidence function Gi is I over 1 plus alpha I to the p. Then, when p lies in an interval 1 and 2, then for this incidence function, we could obtain the local asymptotic stability of the endemic equilibrium. In fact, when p is greater than 2, these two element causes instability of ester. Hop bifurcation occurs. So now this is the application. So now this is it's a paper collaborated by Wan-san, Pan-san, and Kuniya-kun. So this similar condition, we may find FV and V over FV are monotone increasing. And this model has at most 5 equilibria, and we could obtain similar result. So this was the application. And finally, we showed the free boundary problem for the epidemic model. So here is the SIRS model with free boundary problem. The interesting point is that the boundary H moves with respect to the time variable T. The figure of this model is as follows. The interesting point is that the population pressure, due to the population pressure for the infected individuals, the area of the habitat becomes wider. So now for this model, Professor Kim, Lin, and Professor Chan obtained the following result. For the case delta is just 0. So now I am also trying to obtain such a similar result. However, it is still in preparation, but if you have interest on these problems, so let's share the discussion. Okay, this is end of my talk. Thank you very much for your attention.